So thanks for coming to the session. This is a little, I didn't pick the title, it's a little pretentious, but it's basically thoughts about artificial intelligence products, a little bit of history, a little bit of how to develop products. Hopefully we get to an example as well. So first, just who am I? Right now I'm working as the head of artificial intelligence for science, technology, engineering, math at Turnitin. Turnitin is a huge higher education company, 35 million students at over 150 countries. It's been going for over 20 years. It has over 1 billion paper submissions. But I joined it via an acquisition that just closed last fall of a startup called Gradescope. And Gradescope was at first a side project out of UC Berkeley. We were computer science grad students. We had to grade a whole bunch of exams by hand. Even though we were teaching artificial intelligence, we still had to grade paper exams. So we decided to do something about that, build a little website essentially where you can upload stuff and then grade them online, ideally with artificial intelligence. Is the sound good? Cool. So 4 years ago, we started it. Now we have over 80 million answers graded, over 100 or 10,000 educators. Most recently, I was also a co-organizer of the Full Stack Deep Learning program. It's like a weekend boot camp for software developers who are familiar with like the basics of machine learning, deep learning, but want to learn how to ship AI products. And before then, I was a PhD student at UC Berkeley. I was doing research in computer vision and deep learning as well. So that's my background. My goals for this presentation are just reach a shared terminology. I think oftentimes I've sat on panels and stuff about AI, and I just feel like the people are talking about slightly different things, even though they're using similar words. So I just want to get to a shared terminology that we can use. I want to situate ourselves in history, like when did AI get started, what is already accomplished, what's on the horizon, what is potentially no one really knows when it's going to happen. And then how do we actually develop products empowered by artificial intelligence in the current day? So that's the outline. I'm going to start with the history and the terminology. So the terminology, the most kind of big word that people use is artificial intelligence. And that's a really general idea of just thinking and learning machines. Within artificial intelligence, there's a subset of things that are possible that we gave the name machine learning to. And that's making data-driven predictions. Within machine learning, there's a specific method for making predictions called deep learning. And right now, it's the state-of-the-art method. It's inspired by certain biological ideas like neural networks. But really, it's just a name for a methodology of machine learning. And then kind of off to the side, overlapping with a lot of it, is data science. And so the way I see data science is it's applied statistics and machine learning for either data analysis or prediction on data. The types of learning problems that we look at in artificial intelligence, and specifically, I guess, machine learning, is threefold. The first is unsupervised learning. And so what that means is you just have a bunch of kind of raw data that we call X. Could be a bunch of images, could be a bunch of snippets of text, a bunch of sound waves. And the goal is really just to learn the structure of X. Why do we want to do it? One idea might be we just want to generate a bunch of fake versions of that same type of data. Or we may want to find insights without actually like looking for hypotheses ourselves in the data. So for example, this is a fake review of something. The machine learning looked at a bunch of Amazon reviews and then just spat out, like hallucinated essentially another one. So this product does what it's supposed to do, or supposed to. I always keep 3 of these in my kitchen just in case ever I need a replacement cord. So it's like almost there. And this is something called clustering, where data has a certain shape. So like images of dogs, for example, are in general different from images of cats. And that might actually just come out of looking at the data in an unsupervised way, even if you don't know which photos are of dogs and which are of cats. The next type of learning problem is supervised learning. So there you have the raw data X, but then also labels for it Y. And the goal is to learn a mapping from the raw data to the labels, X to Y. And the goal of that is to make predictions. So if I see an unlabeled data sample in the future, I can say that's a dog. So classic example, here's a picture of a cat, and I say cat. Or I just hear a sound wave, and then I understand that it was someone saying, "Hey Siri." This is a super complicated problem because like a cat can be any number of breeds or ages. Could be kitten, old cat, statue of a cat. Could be a picture at night. Could be a picture from profile, head on, from the top. Like the visual diversity is incredible. The audio diversity is also incredible. It could be someone saying, "Hey Siri" in the audience while I'm also saying something. So the sound wave is all, it's multiple audio sources. So it's complicated. And then the third type of learning problem is reinforcement learning. And that's how to take actions in an environment of some sort. So you have an agent, maybe a robot. It takes an action that affects its state or the state of the environment. And the environment might provide a reward. So for example, like an animal might be looking for food. So the agent is the animal looking for food. An action might be like go forward. The environment might respond with saying, "Here's some food." And then your state has changed. Like you found food, you now are satiated. It's kind of a simplistic example. And this is most commonly, you guys have probably seen, Google recently developed a Go playing artificial intelligence that was trained using reinforcement learning. So it's just the agent learned how to play Go just by playing Go against itself forever. This is commercially viable today, supervised learning. And so most people, when they say they do AI, are doing supervised learning. Reinforcement learning is kind of coming to the fore. That's probably going to be like the next wave of commercialization. Unsupervised learning, there's no compelling commercial uses of it just yet. So the history of AI probably starts, with religion and just way down into human history, the idea of like golems and stuff like that. But I want to start in 1950, where Alan Turing, who really founded a lot of computing theory, suggested a test for determining when an AI would be human level, essentially. And so the test is, can the AI convince a human interlocutor that it is also human? So there's someone talking to both a human and an AI, and they can't tell them apart. We say, at that point, the AI has passed the Turing test. So the reason that idea reverberates today is because we still define intelligence functionally, right? So stuff like this, where you confirm you're not a robot, that's a version of a Turing test. And the deeper idea is that there's no philosophical reason to believe that there's anything other than functionality that defines intelligence. And this used to be more of a debate than it is now. For example, the Chinese room experiment, it's a thought experiment where there's a person that's only English speaking who sits in a room where Chinese text is passed into the room, and the person looks at the text, finds a rule in some huge book of like how to respond to Chinese, and then writes out the Chinese characters and then passes them out of the box. So that was a thought experiment saying like, hey, look, this box would maybe pass the Turing test, but it's not intelligent because the person inside of it doesn't understand Chinese. And today, that doesn't really pass muster with AI practitioners. They would say the box is intelligent for all intents and purposes. And if you say that, then there's no real reason to say that it can't be superhuman intelligent. Because a lot of people, I think, when they start thinking about these things, just see humans as like the top of the line in terms of intelligence. But there's no reason to believe that. There hasn't been a good argument for it. In 1957, the Perceptron was developed by someone named Frank Rosenblatt. And they actually built like machines where voltages would mimic what a neuron does. And what a neuron does in the brain is it aggregates inputs from other neurons. And then if there's enough kind of stimulation to it, it fires an electrical impulse down its axon and stimulates other neurons in turn. So the mathematical formulation of it is just this kind of aggregation of inputs, weighting of them, and then passing like either a 1 or a 0 down the line. Today, this is the building block of deep learning. So the ideas of deep learning, even though most of us have heard about it pretty recently, are very old as AI itself. And AI is still informed by neuroscience. It's not, to the same degree that planes are informed by bird flight. We're not trying to replicate neuroscience, but we're informed by how it does things. In the 60s and 70s, we had the first kind of AI summer of like a lot of money coming in, and the first winter of a lot of funding getting withdrawn. And general computers kind of came onto the scene. people got excited about AI, and they had wildly overinflated expectations. So Marvin Minsky is the founder of the MIT AI lab. He said, in about 5 years, we will have a machine with the general intelligence of an average human being. He said that in 1970. He was the person responsible for making that come true as well. Needless to say, they totally failed. And in 1973, there was a famous Lighthill report in the UK that basically said, hey, like, these are all lies. AI is impossible. Let's stop funding it. And that was the first AI winter. And all funding was kind of dried up for AI research. And here's a really cool quote from Marvin Minsky. Our first foray into AI was a program that did a credible job of solving problems in college calculus. Armed with that success, we tackled high school algebra. We found, to our surprise, that it was much harder. And the exploration of the child world of blocks proved insurmountable, except under the most rigidly constrained circumstances. It finally dawned on us that the overwhelming majority of what we call intelligence is developed by the end of the first year of life. And so this is the idea of stuff that we take for granted and learn to do as unconscious infants is way more complicated for a machine to learn than stuff that we take 20 years to learn, like advanced calculus and stuff like that. And this is still where we're at today. Like, there is no robot that's as good as a human baby at just being in the world. 1980s and 1990s, we had expert systems. We had kind of logic languages like Prolog. We had another rise of neural networks, including for self-driving. But overall, they didn't really accomplish much, and there was another AI winter. Today's kind of boom of AI research has really started in the 2000s, and that's when people started using the word machine learning for the first time. And machine learning is really a marriage of statistics and computer science. And it's increasingly informed by big data sets. So whereas in the 60s, people might just have like a room with some blocks, in the 2000s, people had maybe 10,000 images of different photographs of blocks. Main techniques support vector machines, kind of a mathematical technique. The data representation had to be hand designed so that these techniques would work on it. So that would, like a graduate student would develop, like, how do we represent the photo in such a way that it would be like a sequence of numbers that we could then apply these mathematical techniques to. Today, we have like full understanding that data trumps algorithms. So basically, like, most progress is due to larger data. And if you have something that works, you would be better off by adding data to it rather than like fine-tuning the algorithm. In 2010s is when the deep learning came to the fore. And deep learning is really just the perceptrons from 1957, but a lot of them and like arranged in a way such that there's layers and layers of them. And this is better than hand-designed data representations. So now you can actually just feed in like image pixels at the bottom layer, and then the network itself figures out the best way to like extract features from it. And the reason it really came to the fore is a combination of algorithms, such as backpropagation for training these kind of networks, but also increased compute power, super important, and mostly on NVIDIA GPUs, which is why NVIDIA is so successful today, and Bitcoin. And then there's also major breakthrough on challenge data sets in like vision, language, robotics, basically all the fields of AI. At some point in the 2010s, like the winning approach started being deep learning, and it was like an order of magnitude better. It wasn't just a little bit better. And because of that, there's been a lot of VC money and just commercial interest in building applications using these techniques. Now in 2020s, the next decade, we've had 2 AI winters, and it's really unclear what's going to happen. It could be that we just keep getting better and better, and we reach superhuman intelligence very soon. It could be that we realize that like this technique is good for some things, but will never accomplish some other things. And so that's kind of the orange arrow. Or it could be that people just become so disillusioned that they'll want to get out of the field entirely. That doesn't seem that likely. So what's possible today? The first thing to realize is that AI is a moving target. Let's look at a problem, advanced mathematical computation. So before we had a computer solution to it, we thought, well, it's super difficult for us, and it must be super difficult for computers. Therefore, intelligent computers are required to solve it. But after we had a computer solution to it, we just said, well, that's just an algorithm, and there's no intelligence required to solve these equations at all. Chess, the before computer solution for like thousands of years, it was really like a battleground for human ingenuity and logic and insight. But after computers got better than humans at chess, Obviously they're going to be better than humans because they're able to crank through all these computations way faster than us. So that's not intelligence either. Speech, humans are the only really creature that is able to produce and understand vocal speech. Now the computers can do it. We really just see it as, we're just translating between sound waves and text and back and forth. There's no understanding in the middle of it. So what about humor, something that's probably coming up? Like right now, we just can't even have a good definition of what makes something funny. So it feels like it requires good intelligence to generate funny stuff. But I think after a computer is able to generate really good humor, we're just going to say, it's just a combination of unexpected situations and harmless consequences. And obviously, a computer can think of more of them. So we'll just keep moving the goalpost for what we call artificial intelligence. Here's what was possible yesterday. We can recognize handwritten zip codes since the late 80s. The first self-driving car actually drove from CMU to Stanford in 1995. No hands on the steering wheel, no feet on the pedals. The caveat is that it just took a freeway, so it's not super difficult. Beat humans at chess in 1997, Garry Kasparov and IBM Deep Blue. And the Roomba robot, a lot of us probably have, it just vacuums the floor. It is intelligent in some sense. Now, what's possible today? So now we have cars that can pretty much drive on a lot of roads, not just freeways, and in pretty good conditions, or a wide range of conditions, but maybe not the rain or heavy snow. We can beat humans at Go. We can recognize all kinds of handwriting. We can recognize things in people and photos. We can translate from French to English to Chinese, almost as good as a human. We can transcribe speech to text and back. We can generate realistic human faces and other types of images. There's a cool website called thispersondoesnotexist.com. And we can have stilted customer support conversations where maybe the AI will direct us to the right human, but not really handle it entirely by themselves. And in 5 years, I think we'll have cars that can drive most roads and pick up passengers in some places, like special pickup curbs. We'll probably see AI beat humans in a complicated video game, like Fortnite or something. We can generate realistic videos, like Obama saying a bunch of crazy stuff that he didn't say. Generate news articles that are totally no human in the loop involved, but read like a human wrote them. Probably generate realistic music that sounds decent. And probably have whole conversations about customer support with humans not even realizing that it's AI. I think that's feasible in 5 years. Here's what I think no one knows when it's going to come. Cars that can self-drive and pick up passengers everywhere in the world. I think that's a super difficult problem for many reasons. We can talk about it later. A robot that's as mobile and is perceived to be as smart and maybe as loyal as a dog. No one really knows when that's going to happen. An intelligent tutor in all kinds of educational subjects. And I really like Rodney Brooks's. Rodney Brooks is the current head of MIT AI Lab. He has a really good kind of, not pessimistic, but just a realistic perspective. And basically all innovations in robotics that we've had so far in AI have taken way longer than people originally thought. And that's probably going to continue. And that's true for people in the field and outside of the field. But of course, the holy grail of what's unknown is, one, do we have artificial general intelligence? So that's human level intelligence. And then after that, artificial superhuman intelligence. So no one knows this. But people talk about this idea called the singularity that we've probably heard about. Just to summarize what that is if you plot technological progress on some kind of like time versus progress chart, then you see that it's exponentially speeding up. So like the rate of progress is increasing as we go into the future. And there might be a time, according to this theory, that progress basically becomes vertical, like instantaneous. And the mechanism for that vertical progress is theorized to be that the humans will invent a human-level intelligence that will then keep tweaking itself. Because if humans are smart enough to invent AI, then the AI that's as smart as humans can also invent AI, but now they can do it at like essentially much faster than humans can. And so like very soon after human-level intelligence, we'll reach superhuman-level intelligence. And after that, it'll just be like unimaginable progress in a very short time. And some notable people are alarmed, like Elon Musk. I think the take of I don't want to say most practitioners, but a large majority, well, I'm not sure. A large subset of practitioners would advise to not worry about this just yet. It's unclear what to even do about it. It's unclear, there's no timeline on it, and there's a whole bunch of problems that are in the way until we even get to a problem or a point where we should start worrying about it. And part of the reason for this is, people have been predicting that human-level AI is 25 years away since the 50s. And in recent years, people have actually been tempering their predictions and saying, well, maybe it's 50 to 100 years away, experts and non-experts. When you ask people, experts, about specific kind of subsets of intelligence, then you get kind of more tightly bound predictions. So for example, what about a retail salesperson? So someone who can pick up things, scan them, put them in a basket, charge you. So that might only be 10 years away, right? Something like a surgeon is maybe 50 years away. And something that can automate all possible human labor is on average, people say 125 years away, with a huge kind of air bound around it. But it is something we should worry about. Let's worry about this right now. There are a bunch of jobs that probably are going away because they're just so simple, and the AI is going to get there before it gets to a human level or a superhuman level, that I think there will be a huge long-term benefit to this kind of AI coming around, but a lot of short-term upheaval. Just like the Industrial Revolution, we're all better off for it, but it led to a century of crazy political movements and just societal upheaval. So what should we do? I think we are in a great spot to really help because part of the solution is going to be just order of magnitude improvement in education. Like if someone is unable to compete with a robot on something, there's still going to be for a long time something else that they could be doing that a robot is not able to do. And can we help get them there? Probably stronger support systems just so that people can take the time and actually learn, but maybe also radical societal reorganization. So the outline is now, I think we're situated in terminology and the history. And so now we just want to bring AI to our enterprise or start a new startup or something. So the first thing is picking the problem. But let's actually, before picking the problem, just reassure ourselves that it's OK that we're not doing AI 100% just yet, because it is early days right now. So this is a survey from 2018 of a bunch of kind of developers that are doing ML, machine learning, from all kinds of industries. And so what phase are your artificial intelligence projects in today? Production, limited deployment, actively developing, planning, or just kind of feasibility study. And so the production rollout is less than 8% of all the respondents. Most people are still kind of in the feasibility study. So just want to reassure people. But as you start kind of doing the feasibility studies, you're going to be looking at different problems. So how do we evaluate what is a good problem to bring artificial intelligence to? So the first question is automated prediction even valuable in this specific problem? If the problem you're trying to solve is a high-touch consulting, then automated prediction is going to turn people off, right? But if it's something like some back office thing, like accounting, just invoicing or something like that, well, maybe it would be helpful to just automatically do a certain part of that job. Two is, what is the required level of accuracy for this to actually make a difference to you? And is that feasible? And the way you answer that is you look at published papers, you talk to people, you look at other products, you hire people who make strong claims about whether it's feasible or not. And the third thing is, will it move the needle for your business? So AI is going to be harder to ship than you expect. Everyone I've ever talked to, it's taken longer than they thought it would, and it's been more expensive than they thought it would be. So I would advise, don't try it out on something that's not critical to your business. I would either go for something important or just not even try it. Because if it doesn't move the needle, you're just going to spend a lot of resources and time and not really have much to show for it. And the last question is, will you be able to build some kind of competitive moat, which is usually going to be a data moat? The cost drivers of AI development, data availability is the foundation. What is the accuracy requirement that you have? How difficult is the problem, period? So data availability is, how hard is it to acquire enough data? Like if you're doing radiology or something, or tutoring, do you have a way to even acquiring the type of data that you would need? How difficult or hard, or how expensive or difficult would it be? How expensive would it be to label that data? Because the type of data that you'd get is probably not in the shape that you need it to be to actually train AI on. And then is there a unique advantage that your enterprise has to being positioned like in the data? So you might have some proprietary data that no one else has. That's a great place to build AI on top of because no one else can come and kind of unseat you. Accuracy requirement. So there's kind of two ways to think about it. The first is if you make a wrong prediction, if you're wrong about your prediction, how bad is that? So in medicine, it could be very, very bad. In something like a photo sharing app, it's just a minor annoyance, or maybe people don't even notice if you're wrong. And then the second part is, do you even have to make a prediction every single time? Like a self-driving car needs to make a prediction every single millisecond, but something like a photo sharing app, again, doesn't necessarily. Like if you search for dogs on Instagram or something, they might only give you like 20% of all photos that have dogs in them, but that's good enough for you because that's like a trillion photos of dogs. And then the last thing is problem difficulty. So do you see that an academic has developed something on a similar problem or that exact problem that works? And if you don't see that, or if you see it like in the last year, then it's going to be more difficult for you to actually develop it, and there's just more risk it might not work. So I want to talk just a second about accuracy requirement. So ML, machine learning project kind of costs, they scale super linearly with the accuracy requirement. So that means like to get 90% accuracy, you might spend 6 months. To get to 99% accuracy, you might spend 6 years, or maybe it's impossible. And so that's just something to watch out for. But product design is crucial because you can reduce the accuracy requirement with product design. So for example, this is Grammarly, or could be another app that makes suggestions about writing, but it doesn't autocorrect it. It just says, hey, look at this. Is this what you meant? This kind of looks wrong. And then the user can accept it or reject it. Or something like, on Amazon, if I buy something, Amazon doesn't say like, hey, buy this also. They say, here's 10 other things that you might enjoy also getting. And then it's up to me to see if that's useful to me or not. So essentially, they have like 10 chances to get it right instead of just one. And on Netflix, you can also like introduce user interface that makes people feel safe about the prediction. So on Netflix, I might see something that's recommended for me, but I actually like never want to see. But then it says, we're recommending it to you because you watched this other thing. And then I say, oh, OK, maybe I'll go and thumbs down it. And then this is Google Photos. And this is, I think, like the best possible thing, which is like make the prediction, or right before making the prediction, ask the user if the prediction's correct. And it's like super low touch. The user doesn't mind. At least I don't mind. And if it is the same person, then I get value out of it because now they show up in the same album for me. If it's not the same person, I feel good about like not seeing that face in my album. And then Google gets training data. So this is what I want to talk about next, the concept of the data flywheel. So defensible AI right now really just means, or mostly it means proprietary data set. And this is why companies like Facebook and Google open source their AI software and their AI research, like TensorFlow, PyTorch, and like their academic research, because it doesn't matter if other people have access to the same tools as they do, because they don't have access to the same data as Google and Facebook do. Now, data is cheap, like the raw data. You can get like all Wikipedia text, like anyone can get it, or a bunch of images. What's expensive are labels. So what are the images of? What's in the images? You have 1 trillion images, but you don't know what's in them. So usually you have to spend your time and your money to actually label your data set yourself. So this is like satellite data, and I'm sure this is a huge undertaking to like label every building, every road, maybe even every car in a bunch of images to get the AI started. An underrated approach, I think, is synthetic data. So that's the idea that you can generate data that looks like real data from the label. So if I'm training an OCR, optical character recognition system, I can just generate a whole bunch of data that looks like something that a user might take a picture of, like in a document, and upload to my service. But I actually know exactly what it is because I'm generating it from the label. So same thing with self-driving cars. And I think ideally, you have a data flywheel, which is like, you train something on maybe an academic data set or a data set you labeled yourself. You put that in a product, And then you give users hooks to give you feedback on the accuracy of your predictions. And very quickly, you can order of magnitude improve the size of your data set with just user activity. So that's what we call the data flywheel. And I'm actually going to skip this quote. But it's the idea that software ate the world. Like most things that we care about are now in software. But self-improving software is what's next. So the companies that have a self-improving kind of flywheel in place are the ones that are going to win kind of the next phase of the competition. Now, what does it look like for a company to be not driven by the flywheel? You might have product engineering build a product. Users use it. Sales makes them pay for it. Users generate data. Maybe you have a data scientist looking at your sales and your data. And that's kind of it. Now, if you're flywheel driven, you might start by creating a product that already understands what the AI is capable of, builds in hooks to gather data from the users. The engineering brings it to life. Sales sells it. Then the more users you have, the more data they generate. You have people in your company that build pipelines for the data. You have data scientists that look at the data, machine learning scientists that develop more AI models and better models with that data. And then the models improve the product, which gets more users, which gets more data, and it gets this virtuous cycle going. Another thing I want to say is, so most artificial intelligence code is not the actual artificial intelligence code. There's a lot of code around it. Here's a slide from a paper that Google published. And basically, traditional software, people write code, they deploy it as a running system, they write some tests for it, they monitor the running system, and that's it. And it serves like search results or whatever. In machine learning software, you write the code. The code that you write actually trains a model which also learns from the data. So you have the code and the data coming together to create the model. And then you deploy the model as a running system. And then there's a bunch more tests around it and just a lot more kind of code around that whole scaffolding. And for this reason, Google has also called machine learning the high-interest credit card of technical debt. Technical debt being the idea that we can ship features to users, quickly, but by taking on debt that we will have to pay off eventually. And machine learning is a great way to rack up a whole bunch of debt in a very short time. And there's a striking figure in that paper, which basically says, here's all the code in a machine learning system. And the black square in the middle is the amount of code that's the actual machine learning code that a machine learning scientist would write. But then there's a whole bunch of other stuff around it that's necessary, like data collection, data labeling, feature extraction, resource allocation, stuff like that. That's just necessary for the AI model to work. I actually want to get to Q&A, so I'm going to skip this. But there's a whole bunch of kind of AI-specific tooling and infrastructure that you should know about as you embark on developing AI. And because there's so much kind of new stuff, people have come up with all-in-one solutions. And it really started with the big companies like Facebook, Google, Uber, publicizing their all-in-one in-house machine learning platforms that go all the way from data to deployed model. And now there's a bunch of startups like Domino Data Lab, for example, that kind of productize that for people like us, startups and other companies. And Amazon SageMaker is another example of this. And so I just want to really quickly cover what it is. So it's like data. This is FB Learner Flow, Facebook Learner Flow. So every model that is shipped on Facebook kind of goes through the same type of shared platform. You got data, extract features, train models, deploy it somewhere where it makes inferences, and then gather feedback from the users to add to the data and keep going around. You can track the experiments you're running. You can look at what kind of model you're training and kind of debug it that way, and so on. The roles that are important in the AI enterprise are data engineer. The function is to build data pipelines, aggregation, storage. They really produce the data system. Machine learning engineer is kind of a new job title. What they do is they train and deploy production-grade machine learning systems. And so the overall prediction system is their responsibility. As opposed to the machine learning researcher or scientist, whose goal is to develop research-grade prediction models. So things that don't necessarily have to run at scale, but things that just have to be better than the previous thing. And their work product is just new models or improved accuracy on existing models. Now, data scientist, I think I don't want to maybe say bad, but like at old organizations, it would be one person doing all of the above, like data, engineering, and research. And that used to be called data scientist. I think the new consensus for what a data scientist is someone who cares about the business value of data and answers business questions with data. Data engineer could be a software engineer with like just machine learning interest. Machine learning engineer is usually someone who's taking courses in machine learning, or maybe a grad student that wants to do software engineering. A machine learning researcher is super hard to hire. There's like a AI talent gap, but it's usually a PhD in like the relevant subject that you're working on. And then a data scientist can come from a wide range of backgrounds. Often it's a physics PhD or a cognitive psychology PhD that just learned a bunch of skills. They're not necessarily very good on software development skills. They know enough machine learning to like ship stuff, but not as much as an ML researcher. I'm going to skip this. I was going to give an example, but I actually want to stop here and then take questions and answers. So thank you. You guys have any questions?
Where do you see areas for application? Where do you see areas for application for AI outside of your focus across the education spectrum?
Well, I mean, there's a lot of. I kind of avoided saying much about education because you guys have stronger opinions about that I don't want to step on toes. But there's a bunch of applications of AI in education. I think what's crucial for us is picking a product or like designing the product such that we're tolerant of not perfect accuracy. So if you're designing something that's replacing an instructor, you really have to be 100% accurate, as good as an instructor. If you're designing something that just helps an instructor or helps the student, but doesn't fully replace it, then you don't have to be as accurate. So I think that's key for like deploying stuff in the short term. We still have 2 minutes according to this clock. Yep.
Can you go back to that slide just before this that you skipped over?
Oh, the hiring?
Yeah.
Yeah, so I kind of said it, but data engineer is really just a software engineer that's kind of focused on big data ops. ML engineer would be someone who's a software engineer first and then took an interest in ML, took boot camps, took online courses. Or it could be a PhD or a master's student that has experience in machine learning, but is interested in just writing good code, clean code. ML researcher is like super hard, huge talent gap. Data scientist would be like a perfect one, would be a physics PhD, just a smart person that's able to figure out a bunch of stuff. Yep.
How far did you get in applying ML to Gradescope? And if you hadn't sold it, where would you have wanted to have taken it?
So we assist the instructor in grouping student answers as they grade. So when the instructor has to grade a bunch of student answers, some student answers are basically repeats of other student answers. And our goal is for an instructor to never see more than one unique answer. That's how we apply AI. And our goal for expanding AI is to just apply it to more and more complicated question types. Like potentially at some point, even essays. Like can we cluster essays in a way that the instructor still decides how to grade them, but they don't have to like, they can deliver feedback at scale, essentially. All right, maybe last quick question. Yeah.
So we work in Turing team, and my question is how close we are to providing writing assessment or writing essay tutoring with AI or anything that helps it.
I think there's two questions maybe. Like, can an AI write a good essay? And then can an AI grade an essay written by a human? I think an AI can grade like an SAT essay on an SAT scale, like 1 to 5 or whatever, because those are such big buckets. And that's actually what's done. Like SAT essays are graded in part by machine learning. But to deliver like precise feedback, I think we're working on it at Turnitin, but to really replace an instructor I don't want to make a promise. I think we're focusing on providing suggestions to the student and suggestions to the instructor, but not replacing them just yet. And then for writing essays, it's probably within the next 5 years, we'll see like really realistic news articles written entirely by AI. So, and that could mean essays as well. So that's kind of scary, especially for Turnitin with plagiarism. Like, is it, it is plagiarism still if you have an AI write it for you, but it is a different type that we'll have to deal with. All right, well, that's my time. Thank you all.